Good morning, everybody. First of all, we have a terrific Codeforces round today. We have round 741. It's a Div 2 only round. Second of all, I just want to say, listen very carefully. You hear that? No, exactly. That's the point. We have grade A audio today. Should be terrific. So I'm excited about that. I guess a couple announcements we'll do before we start the round. So we can start a little bit late since although there are a lot of problems, it's not rated for me, so it doesn't matter too much. We'll have solutions at the end of the video if you're interested in those. That's an announcement everyone expected. Next one, today's my birthday, so hopefully it's a fun round. That should be fun. And the next one is, I know this is not like an official announcement, but if you're interested in it, make sure you sign up for Facebook Hacker Cup. The qualification round will be this weekend. It's a super cool contest. And yeah, good luck, have fun if you're competing in it. I obviously can't compete because I work for Facebook, so that would be bad optics. But definitely sign up if you're interested in it. And hopefully you enjoy the qualification round. It'll be 3 days, so it'll be Friday through Sunday. Maybe different a little bit depending on your time zone. But you can check, if you look up Facebook Hacker Cup, you can check all the details on that page. So good luck if you're competing. And good luck on the Codeforces round if you're competing in that. All right, so let's start with problem A. What do you say? The miracle and the sleeper. Actually, let's clean this up real quick from the contest yesterday. All right. So you're given two integers L and R. We want to find the largest possible value of A mod B over all pairs A and B, for which A goes up to this. All right, gotcha. So B has to be smaller than A. So we probably want to make A the smallest value possible, and then B either the biggest value possible or A times 2. Nope. Make B either A plus 1 or A times 2. Wait. A mod B, so A and B can be the same. Oh, the largest possible value of A mod B. Yeah, so either the biggest value or B times 2 minus 1. So I guess that's not true. So we probably want to make B as big as possible and then A 1 less than half of it if possible. So 26 and 14 would be 12. Yeah, okay. Makes sense, I think. So so if B is odd, this works. What if B is even? Then we want, so I think we just want B over 2 plus 1 actually. And then this out B minus A. How does this do on samples? Come on, Codeforces. Not quite right. So if A is less than or equal to B over 2. Yeah. Looks good there. Oh, we're not registered. Okay, can we register late? We can register late in 20 seconds. I guess we'll read B and then register. How about that? All right, during the hypnosis session, which hypnosis session? Was this flavor text on A? There is no hypnosis session. Okay. Nicholas suddenly remembered a positive integer n, which doesn't contain zeros. Soon he returned home. He got curious, what's the maximum number of digits that can be removed from the number so that the number becomes not prime? That is, either composite or equal to 1. For some numbers, doing so is impossible. For example, for 53, you're always going to be prime. Note that you cannot remove all digits from the number. So it's up to a 50-digit number. Okay, interesting. Well, yeah, so if you have any, so there are a bunch of numbers that you can have just one of, and if you have two copies of any number, then you're good. But sometimes you might not have two copies of the same number. That is true for up to like 10 to the 10. Yeah, so you can have up to 9 different numbers, right? You can have 1 through 9. And, oh, but then you'll only have, if you have 1 through 9, you'll only have, like, you'll have one number that's even or a 9 in it. So you have an even number or a 9. So if you don't have an even number and a 9, the only numbers you have are 3, 5, and 7, right? Those are the only, in 1, 3, 5, 7. So you have 1, 3, 5s, and 7s, which you might be able to have 2 of, possibly. So you can have at most 4 digits that are interesting. Once you have more than that, the answer is either 1 for sure, or it's 2 because you have a duplicate. So I think we can just check all of those subsets of those 4 numbers, and then that should be fine. Yeah. I think that should be good. Let's register. All right. Problem B here real quick. While we submit. Nice. Gotta love it. All right, problem C, problem B. So, yeah, we got some test cases, we got some stuff. All right, so let's try some numbers up to 10 to the 5, maybe? Or I guess that might be a bit much. Well, I guess we only need all 3-digit numbers. Or itself, yeah. Can the answer be 0? Oh, you print the smallest number you can have left. Gotcha, okay. So static Boolean is, I guess let's just pre-comp the is prime. So for int I equals 2 less than x I plus plus. So if x equals, or if x is less than 2, return false. Otherwise, do this stuff and then return true. And let's say I times I is less than or equal to x. All right, and then if x mod I is 0, return false. So now we can check if some things are prime. Let's pre-comp all this. How long does this take? probably fine. I guess we'll do this just to be safe. Okay. So what if there are no solutions? Oh, it's possible to delete some digits to obtain a not prime number. Okay, that's interesting. Makes it much easier. So you can always delete some digits. Yeah, so that if you can always, that should mean the answer can't have more than 4 digits. The answer has at most 4, the biggest answer. So yeah, int best equals 0, I guess. Okay, so if, I guess this needs to be a string. And for int small equals, wait, you want to have the number left be not prime, yeah. So small equals 1, small is less than prime dot length, small plus plus, or small is less than 10 to the 5th. Small plus plus. If not contains big, well, I guess if is prime small, continue. Oh, this needs to be not here. So do the pre-comp, we can handle this, do our test cases, get the input. If not contains big, small, then continue. Otherwise it contains us, we're a prime, and there's no answer smaller than us. So ans equals small, and then break. And then we should be good. Yeah, so we just need this contains method. So string me equals x plus empty string. Int me end equals 0. So for char c in s dot char array, and return me end equals me dot length. So then we go through each character in the string, and then if we match, we move on. So if c equals me dot char me end, that means that we should move toward the next character in us. And then we're good. Cool. Let's try this. Nope. For lots of reasons. What's wrong with this? 3 is not prime. What? Oh, it's the number of digits. $227, 4. This is dumb. This is so dumb. Why? Ah, okay. So you just print the length, I guess. Okay. Right. 227, 14, 12. See some other numbers. The answer is 16. If there are multiple answers, print any. Looks good. Yeah, cool. One is legal, I think. So we should be good there. All right. Let's move on to problem C here. Rings. Frodo was caught by Saruman. Okay, we'll skip this for a minute, and then maybe you'll come back to it in a bit. Somewhere in the parallel Middle Earth. Looks like we got it. Nice, nice. Brilliant. All right, somewhere in the parallel Middle Earth, when Saruman caught Frodo, he found N rings. And the ith ring was either gold or silver. For convenience, this person wrote a binary string of N characters where the ith character is 0 if it were gold, and 1 otherwise. Saruman has a magic function f, which takes a binary string and returns a number by converting it into a binary number, and then converting the binary number to decimal notation. Yeah, so you've got, okay, so it's just like, you take a string, and then if that were a binary number, what number is it? However, Saruman thinks the order the rings are placed plays an important role. He wants to find 2 pairs of integers, such that can you describe this in English, please? Okay, let's try and read the math. Okay, so L1 is less between 1 and n, R1 is between 1 and n. The difference between them is bigger than or equal to n over 2. And then we find another pair of integers, and the difference between them is bigger than or equal to n over 2. And these 2 pairs are distinct. Oh, but they aren't totally distinct, so they can overlap in one number, but just not both. Let T be the substring from the first range, and W be the second substring. Then there exists a non-negative integer K, such that one is a multiple of the other. Don't say this, guys. Okay, quick rant time. Don't say it is guaranteed that X. It is so annoying. Like, say it can be proven that X. I think what they mean here is that given the constraints of the problem, this statement will always be true, whether they had this in the statement or not. I think that's what they mean. But when they said it's guaranteed that X, it sounds a heck of a lot like the guarantee they make in B, which is this thing, which is if this sentence weren't here, this wouldn't be true, right? It is very unclear whether if this sentence were removed from the statement, it is very unclear whether this would be true or not, because I haven't spent time thinking about this, so I don't know. Maybe if you're just like infinitely smart, you can be like, oh yeah, of course this is the case. But for me, and for people who like are new to solving this problem, it's not clear whether this is a universal truth that's like could be inferred, whether they didn't tell us or not, and they're just saying this to like make us avoid the situation of thinking what would happen if it's impossible, or if this sentence is an important part of the problem, and if we misread this sentence, then we'd be like, wait, it's totally possible. Like here's a case that's where it's impossible, but without the sentence, we wouldn't know what to do in an impossible case, right? But like, or because of this sentence, this case, which would otherwise be impossible, can't exist. So now what I'm going to do here is sit down and think about whether, like, what this sentence is supposed to mean, because it wasn't clear enough. So that's my one, like, please, problem setters, please do this in the future, because it's just like, it shouldn't be difficult to understand what the problem is asking, you know? That's my pet peeve. Yeah. Anyway, okay. So let's think about it here. So we have a binary string, and we want to pick 2 substrings that overlap, possibly, where one is a multiple of the other. Am I understanding that right? Yeah. So If we have a 0 in the second half, right, we can just choose the first prefix and then the second prefix. Anything longer than that? So what if, yeah, we can just choose like this, and then this times 2 be shifted over 1. A non-negative integer k. Oh, so f of t could be 0. Oh, yeah, so here's the thing. You try a really long string like this, right? Yeah, I guess try this, and then try it shifted over by 1, and then they might match. That's a good question. Yeah, what if they match? Oh, so if we have any zeros, if you have a 0 in the first half, yeah, so okay, let's say it's even length for simplicity. So if you have a 0 in the first half, if you have like 0 and then 1, 1, 1, 1, then you can do this, and that works. So greater than or equal to the floor of NR2. So if there are any zeros in the string, yeah, so we can handle if there are any zeros. And if there are no zeros, then we can do 2 strings. Like any 2 big strings. Yeah. Nice. That's a cool problem, actually. I really like that. So we'll just read in the array. Okay, so then for, I guess, in index is -1. So if it's less than n/2, I think would be one thing. Probably have something else. So if this is the case, sys out 0 plus n minus 1. Oh, we gotta do this one indexed, huh? Yeah, so let's just make a print method. In this case, print 0, n minus 1, 0, n minus 2. If it's all ones, that should be fine. Yeah, and then, oh wait, they're all ones, and then this is 1 to n minus 1. What if there is a 0? So this is, okay, so if it's 4 long, then that means 0 or 1. If it's 5 long, that means it's in 5/2 is 2, so it's in 0 or 1. Yeah, okay. So in this case, print z index to n minus 1, and then z index plus 1 to n minus 1. Otherwise, print 0 to z index, and then print 0 to z index minus 1. So 2 to 6 and 3 to 6. 2, 3, 4, 5, 6, and then 3 to 6. Sounds fine. 1. We have 1 to 6, 1 to 5. 1 to 6, and then 1 to 5. I think that should be fine. Let's try submitting this. Then we'll see what happens here. Ten minutes solve first problem, 10 minutes solve second problem, 10 minutes solve third problem. Pretty consistent, at least. All right, looks like we got it. Nice, nice. Very cool. All right, so let's read problem D then. How are the standings looking? I'm like 10 minutes behind people, so this is kind of nice. You gotta like that. Ooh, man, this is really hit a wall here. I guess maybe a slightly smaller contest than usual, but wow, is D really that hard? Okay, didn't see that one coming. Let's read it. This is the easy version of the problem. The difference between versions is that the easy version does not require you to output the number of rods to be removed. Oh, gotcha, okay. Stitch likes experimenting with different machines with his friend Sparky. Today, they build another machine. The main element of this machine are N rods arranged along one straight line numbered 1 to N inclusive. Each of these rods must carry an electric charge quantitatively equal to 1 or minus 1. Otherwise, the machine will not work. Quantitatively equal to. In other words, equal to? Other than quantitatively, how are things equal? How else are numbers equal if not quantitatively? That's a good question. I would like to know that, please. Quantitatively equal to, man. Oh boy, all right, this writer. Oh, and there's a mistake. In both versions, there was an issue with the note section. Okay, listen. Quantitatively equal. What a, oh boy. What a great writer. I love it. I love it. No, actually, it's a good contest. The problems are interesting. I've actually liked it. I'm sorry for disrespecting the problems. So just don't say, don't guarantee things, and quantitatively equal. That's great. All right, I'm gonna start using that. Another condition for the machine to work is that the sign variable sum must charge on all rods. Oh, sum of the charge. Okay, so you got a bunch of ones and zeros. The sum of them is 0. More formally, the rods can be expressed as an array of n numbers where the sum is 0. Okay, yep, this is... What? Oh, what? Okay, this is interesting. So this is non-trivial. So it's not the sum of the elements is 0. The sum of, like, if you flip them. Okay, well, thank you for explaining this. Sparky charged all n rods with an electric current, but unfortunately it happened that the rods were not charged correctly. The sign variable sum is not 0. The friends decided to leave only some of the rods in the machine. He asked Q questions. In the ith question, he asked, if the machine considered rods with this number, what's the minimum number of rods that could be removed from the machine so that the sign variable sum on the charging ones would be 0? Perhaps the friends got something wrong and the sign bits is already 0. In which case you don't have to remove any rods at all. If the number of rods is 0, we will assume the sign variable sum of charges is 0. That is, we can always remove all rods. So do you like remove them and then put them back somewhere else? Like, because you could swap 2 rods and that would change the sum by 4, right? Like if you have a +1 here and a +1 here, or a +1 and a -1. Initially you have +1 +1, but you change it to -1 -1, so you've just changed your sum by 4. Or do you just take them away? Let's read the sample. In the first case, for the first query, you can remove the rods numbered 5 and 8. And the following will remain. It's easy to see that the sign variable sum is 0. So the first query is 1 to 14. So just this entire thing. So plus 2, let's look at this, okay. So they removed probably this one here. And then this one here. Yeah, okay. So that's what it was before. They removed some things, and then you get this. Looks right. So what does this actually look like? So we have plus, plus. I guess let's just keep, so we want to flip every other one. All right, so we have 3, 4, 5, 6, which matches up. Okay. All right, so I think I see. So the minimum number of rods to be removed is just the sum. Yeah, so it's just the range sum. And what is the difference here? What is E2 like, or D2? The numbers of all of these rods. There can be a lot, right? The sum of answers does not exceed 10 to the 6. Okay. Okay. So we just want to know, this seems like a little bit of a boring problem, right? We just want to know the positions of the things to remove. Remove the things at position 1 and 11. So they give us samples. In the first case, for the first query, you can remove the rods numbered 5 and 8. But they don't, right? Oh, they do. They remove 5 and 8. Yeah. Okay. All right. So, yeah. So we just want to see whether I guess we just have to offset it depending on whether we start at an even index or an odd index. Because at even indexes, things start positive, but at odd indices, they start negative. So we can handle that. That shouldn't be too bad. Yeah, let's just solve D1 first, and that should be pretty easy. So for D1, the parity of things doesn't even matter at all, right? So we can just handle that pretty quickly. And then we want char array line equals this dot char array. And then int array cs equals new int array n. So I guess int array delta, but I guess let's just make a. New int array n, and for int I equals 0 less than n plus plus, line at I equals, I guess just, sorry, a at I equals line at I is a plus. If that's the case, give it a 1, otherwise it's a -1. All right, and then CS will be n plus 1. So for int I equals 1 less than n plus equals 2, a at I times equals -1. and then go through CS. And we want to go through our queries. So for int q equals 0 less than q, we'll say that out math.abs of, I guess we need the L and the R here. So math.abs of CS at R plus 1 minus CS at L. And that should be good for this. So two, not 4, okay. So I'm saying the answer to this is 4, but the answer is 2. For the first query, we can remove the rods numbered 1 and 11. Okay, so let's try this again here. So we got this. Oh, because when you remove it, things change. Yeah. Okay, that's interesting. It was harder than I thought. Yeah, like once you remove, if you remove something, you've just like inverted which things are positive and negative after you. Yeah, so every time you remove something, you flip the sum. Okay, I see. Good, good. So how do we handle this? When you remove something, you'll fix the sum kind of. Will you? Do you fix the sum? The answer ever bigger than 2? I hypothesize the answer to that is no. The answer is always at most 2. Yeah, you have a lot of freedom with what you can do. So if it is 0, oh well, can we just min this with 2? No, we'll miss some 1 cases, I think. Let's actually just look at what we were printing versus this and then see pattern find here. It's basically even odd, even odd, even odd. Yeah, okay. So we'll just get D real quick and then figure out why it's right in a minute. So if ants is greater than or equal to 2, Okay, so this should be right. Do we need a print writer? We do. All right, so that was a clever misinterpretation of the problem we had right there. See what happens here. Okay, this is a cool problem. It's taking a long time to judge. All right, we got it. Thank you for the good samples. I appreciate it. I don't know why that's right. I have a little bit of intuition, so it's gonna work for 0. Yeah, okay. So the 0 part is obvious. If it works, the answer is 0. Okay. So now, if the answer is actually 1, oh, I think I see. Yeah, so let's think about this for a moment here. I think we should be fine. So cool. So here's the idea. So let's say we have like some 1s and -1s. All right, let's do pluses and minuses. So initially what'll happen is everything on the odd positions will get flipped. So let's look at the prefix sums here. So prefix sum, we've got 1, then this is odd, so it's really a plus, then we have 2. This is, okay, so what values do these contribute? So 1, then this is really a 1, then this is a 1, this is a -1, the -1, -1, -1, -1. Yeah, okay, so this is nice and easy, I guess. So 1, 2, 3, 2, I guess we have a 0 here, 3, 2, let's clean this up a bit. We have 0, 1, 2, 3, 2, 1, 0, -1, -2. All right, so this is the string we're looking at. Now, if we were to remove something, say we remove this, what changes here? we don't get this -1 anymore, so we lose this. And then also, for everything after this, the thing that's like flipped gets changed, right? It gets inverted. So this suffix after it gets flipped. Which means effectively, so the prefix sum here is going to be equal to 1. And then, oh, so for 2, it's always possible you just remove the very last thing. Okay, so that's how. So we know the sum then. Let's remove this last thing here. Like this. Now we'll solve this case. So now the sum is odd. When we remove something, we'll make the sum even. And we will flip all of this. So this sum is +1. We want this sum to be +1 as well. So we want to find a time where the prefix is half, right? So where the sum before you is equal to the sum after you. Yeah. So that's always possible. Because if your sum goes from 0 to like 11, and like this, it changes by 1 each step, which means it has to hit 5 somewhere. Okay. So the question is, how do we find that? At least somewhat quickly. Well, I mean, we don't even have to do it. We can do all the queries offline. Yeah, we can do the queries offline. So we can just, yeah. Okay, sounds good, yeah. We can just do the queries offline. I don't know that I really feel like typing that, but we can do it. How about we just read E, and then we'll think about it for a bit and then go back to D2. Okay, so string expansion is just you just take a string and then repeat it. Okay. Oh wait, never mind. So you get a sequence of the following strings. Oh, just all substrings? Gotcha. You just get all substrings. To open this, or you must find the size of the lexicographically largest subsequence, the expansion of a string S. A string A is lexicographically smaller than B if this happens. What is a subsequence? Unremoved elements. Yeah, we'll ask. Doesn't hurt. Okay, so this is getting lots of solves because it's easy. So suffix arrays, question mark? Yeah, you've got 10 to the 4, so tricky on time, but you have just some big array, right? If you have just this array, expansion of S, the size, yeah. Well, like if you had, let's say you had the expansion sorted, right? Then it's just longest increasing subsequence, which is n log n, on this choose 2. This sounds dumb, right? Like, if we can run suffix arrays to sort these, and then once we have that, we just find longest increasing subsequence. Well, I guess increasing. So, yeah, so they can't be the same. Maybe that part's tricky. We can't have ties. I guess it's not trivial. Well, no, it is. You just only include the things that are bigger than your longest common prefix with the previous element. Because if it's a common prefix, then you just ignore it. And if it's bigger than it, then it's fine. Then it won't be double counted. Yeah, this should be easy. Okay, so we can do that. We can do this. Should we read F? Find something we don't know how to do. Do you know what tubular bells are? I don't, actually. They're a musical instrument made of cylindrical metal tubes. In an orchestra, tubular bells are used to mimic the ringing of bells. That's kind of neat. Mike has tubular bells too. They consist of n tubes. Each of the tubes has a length that can be expressed as an integer from L to R, inclusive. It's clear the lengths of all tubes are different. It makes no sense to make the same tubes. If you say so. It's also known that the difference between the biggest and smallest is equal to n, or the number of tubes are n. Gotcha. So there's like a continuous range where they have all lengths. Formally, we say that Mike's tubular bells are described by a permutation A of length n that contains all the numbers from L to R inclusive, with AI denoting the length of the ith tube. You are offered an interesting task. I love interesting tasks. To guess what Mike's instrument looks like. Simply, you must guess the permutation. Mike won't tell you L or R, he'll only tell you n, and you can ask, at most, n plus 5,000 queries. In each query, you'll give the name of 2 positive integers, x and y. In response to this query, the program written by Mike will give you, so they can't be equal, yeah, will give you the LCM of ax and ay. Oh, so it's a permutation as well. Lowest common multiple. Yes. Okay. Thank you. Appreciate it. It's guaranteed that the sum of maximal number of queries doesn't exceed 10 to the 5th plus 5,000. Yeah, okay. I think I see. Is this interactive? It's not adaptive. I wonder if this is abusable. So, you got some permutation of numbers. And, well, if you pick a bunch of random numbers, if you pick a bunch of pairs, you're probably, the GCD of those pairs is probably going to be 1. Yeah. Yeah, probably. Right, like, it's going to be 1. It's going to be 1. It'll be 1. These are up to 10 to the 5th, okay. So the LCM is at most 10 to the 5th. I wonder what % of numbers are coprime. Probably, oh, a small %. Like all even pairs are not coprime. Yeah, I don't know. Okay, that's non-trivial. So let's go read D2 here and then solve it, I guess. Okay. Yeah, okay, so I guess let's just start with this code. D2. Okay, so if this is 0, print this. If it's 1, we gotta find out why it's 1. Well, let's just make our query class. Static class query implements comparable query. LR ants public query int L int R int ants. This dot L equals L, this dot R equals R. Then public int compare to query O. Return integer dot compare L to dot L. All right, so we have this. So now we need a bunch of queries. And then sorted at this equals this equals this. We don't need to pass in the answer. All right, so now we need to arrays.sort the sorted version, then go for query QQ in queries O. And then sys out O dot, I guess, or print writer out. Out dot print line QQ dot ans. Oh, and then we need the answer positions. Yeah. Okay, so I guess if it's, yeah. Print this if qq.ans is not equal to 0, then sys out okay. So now we need to process these queries. So we have them sorted by L, yeah. So now we want to say, when is the next time the sum becomes X? So yeah, we can just process from right to left. So int array next time sum is equals new int array n times 3. In offset equals n times 3 plus 100 over 2. All right, so cool, because we might need to put negatives here. All right, so now we need to process everything from right to left. Do we need this? I guess we just need each of the queries at each position. Yeah, that's probably easier. We don't need this, we don't need sorted, we don't need this, we don't need this, we don't need this. All right, so then we'll say queries at L dot add queries O at QQ. What's wrong with this? Oh, this is query. Right. Okay, so then for query QQ in queries at I, let's rename this to L. So int R equals QQ.R. So if CS at R plus 1 minus CS at L is equal to 0, then QQ.ans equals 0, and then continue. All right, so what if this, if CS at R plus 1 minus CS at L mod 2, if it's an even number of things, that means we have to remove 2 things. Then QQ.ans equals 2, else QQ.ans equals 1. So in this, let's say QQ dot remove or dot ans positions equals we don't know. And then this will be qq.r. We'll remove the last one. Otherwise, this will be just we don't know. Okay, now we need to find the position we remove. So we have the final sum. We want to know when the sum is the first time it's, yeah, so let's say the final sum is like 5. Oh, in this case, we should probably say r minus minus, because we're removing the last thing. Okay, so the final sum is 5. Equals 0, 0, null. So then we want to see when it equals 3. All right. Yeah, because you remove the 3. This part after u is 2. The part before u is also 2. Yeah. Okay. Same thing if it's negative 5. So in target final sum will be final sum over 2 plus final sum mod 2. We want to find the index that it's this. So the next time the sum is CS at n equals n. So we'll say, yeah, the next time the sum is whatever it is, print this. So next time sum is at CS at L equals L. It's gotta be, yeah, it'll be here, so we don't need to worry about it existing. And we figured out this too. Okay. So now we just need to say when does this occur? So target final sum plus equals CS at L, because we would subtract that. Yeah? Yeah. Oh, and this needs to be plus offset. So then qq.ans positions at 0 equals target final sum equals next time sum is target final sum plus offset. Looks good. Then we should be fine. Okay. I think this works. This needs to be different. Okay. So yeah, that should be fine. These are all 0 indexed. Does this work? So remove index this, and then they said remove 3. 1, 2, 3. So what is this? Plus minus, or plus plus, plus minus, minus plus, minus, minus, plus, minus, minus, plus. So 1, 2, 3, 4, 5, 6, I think, and then we should be fine. Okay. We can try it. Let's give it a shot. If we don't pass samples, then it doesn't hurt us anyway, so. And it takes the nice side effect of I don't have to. Okay, well, let's read the thing. What does it say? Sum is not 0, test case 1. Yes, it is. Fake news. It is 0. Yes, it is. I don't believe you. Okay. Oh, that's my code. What is test case 1? First test case is this. Remove index 2 and 14. Oh. Okay. Index 2, huh? So what is the sum now? So let's flip every other. Is that true? Yeah, okay. So that one, this one, this one, this one. Yeah, looks fine. So what is the current sum? So 1, 2, so 0, 1, 0, so it's 2. So we want the first time the sum is 1. It's not 1 there. What is sum? 0 or 1. Oh, it is 1 here. So if we just remove the first thing, that would fix it, right? Oh, we got to remove 2 things. So remove the last thing. So the sum is 1. So just remove the first thing and then we're fine. Or remove the second thing. Remove index 2 and 14. Oh, when we remove index 2, this all flips. Okay, what is the sum here? Oh, -1. All right, let's print some stuff here. So this is what I was looking at, or what was I just looking at? I think this thing here. Final sum is 1 after we remove a minus, but that's really a plus, so it should not be 1. 0 to 12. Why is the final sum 1? Oh, because you removed this, so it should be 1, right? 1, 2, 3, 4, 5, 6, and then 5, 6, 7. Yeah, and then 1, 2, 3, 4, 5, 6. So it should be 1. The sum is 1. Okay. So you want to remove something where the sum is 1. So if you remove any plus, that should fix it. Right? Or do you want the sum from the right side? Well, it shouldn't matter. When the sum is 1, anytime the prefix sum is 1, you should be fine. Oh, so here the prefix sum is not 1. Here the prefix sum is 2. Yeah, okay. So why is this wrong? So we want to find when it is this minus this. Oh, because we need to add 1 to it, I think, right? Here the prefix sum would be 1. Here it would be 1 too. Why does it not print this? Next time the prefix sum is 1. That's index, oh, the next CS index. Yeah, so this minus 1. 1 and 14. I think that should be fine. Okay. Seems pretty plausible. I'm gonna get TLE'd here. That'd be kind of annoying. I think we should be fine. Geothermal got it a bit ago. Yeah, nice. What? How far are we into the contest? Oh, we're far. All right. Well, yeah, okay. E shouldn't be too bad, I don't think, right? So, yeah, if we just do suffix arrays on this, we should be good, I think, right? So that's the idea. Do suffix arrays and then find LCP. Okay, I have to go check that real quick. But yeah, I think we should be good to go here. I think. So let's run suffix arrays on this. We get this, then that, then we get the B, BAC. Then we get this small c first, and then we get C, B, AC $. So here's our suffix arrays. So yeah, from smallest to biggest we have A, AC, ACB, SCOTUS judge, that, 0, this, that. Yeah, should be fine. Okay. Cool. Seems kind of easy, but we can do it. Oh, do I not? I don't have suffix arrays yet. All right, back to the UCF hack pack. Suffix array. Oh, we want suffix array fast. This is so long. Oh my goodness, this is ridiculous. Okay. Okay, so we have the suffix arrays, and we should be good. Yeah. All right. So we need this multi-test case. Int equals this. Char array line equals this. Int array index of substring equals new int array n by n. Okay, so this will set the current index of the substring we're interested in. Yeah, good. So we should be fine there. So then what do we need after that? Yeah, okay, so we have all these substrings, good. So then we need to run suffix arrays. So int SA will be suffix array of the line. And then we need LCP equals LCP. We don't need rotation array. Yeah, suffix array, and then the line. Well, I don't, yeah, we shouldn't need rotations. Okay, so we have this, we have this. So now we need int array A, new int array. Well, it's an array list. Okay, so now for int L equals 0, less than n L plus plus. I guess no, that's not right. So for int I in 0. Yeah, so now int skip will be I equals 0. If this is the case, we skip 0 things. Otherwise, we skip the LCP of I minus 1. However many we match, yeah, that's how many we skip. For int r equals skip. Okay, so int L will be suffix array at I. And then for int R equals L plus skip, R is less than N, R plus plus. Interesting, substrings dot add index of substring from L to R. So now we have I guess we probably just want to mark this as the value of the substring. Yeah. So we'll skip this for a moment. The value of this substring from L to R was cur in plus plus. Oh, is this right? So we might have a problem, right? We do have a problem. This right here. Yeah. This substring here, we're saying you can use this A, but you can't use this A. You might want this A. So we need to like mark these are equivalently good. Yeah. Okay, how do we do that? So to mark, we need like a stack. Of like LCP long. Okay, so what do we do about this? So we have the suffix array and the LCP. Yeah, we want to, okay. While not stk.is empty, this needs to be an int array. Okay, so stk size equals math.min of stk size or skip. is less than L plus skip R plus plus. So then value of substring from L to R equals STK at R minus L. Yeah, okay. And then this is the same as STK at STK size plus plus equals this. Yeah, okay, looks good. Looks good, I think. And then we should have our array then. So it's n and n minus 1, n minus 2, so this is n times so for 2 you have 1, 2, 3. So 2 times 3 plus 1, or 3 over 2. Okay. Alright, let's see if this is reasonable. Well, I guess let's just do the one case here. So 1, it's AC, B, AC. Is that right? AC, B, AC. Looks good. Oh, we need the length. So 5 and this. We're crashing. Why are we crashing? Value of substring at I. Okay, so not what we're looking for. So we're only looking at used parts of the stack. So what's going on here? Should we try simpler string? So 1, 3, ABC. Yeah, we're missing some. So we're missing 2, 2. 3, 0, 3, 0, 1, 2, 3. Why 3? The $sign. Okay, what if we get rid of that? Okay, what if you have ABA? Then this comes first. Should it come first? Probably, right? Yeah, it should. Yeah. Okay. Yeah, that seems plausible. So what does this look like now? So we have 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, you could just do, that works, but you could also do this. Yeah, okay. So I think we're fine. Okay, so now we need static int LCP, int A, int array A. Okay, so we want to find LCP. No, not LCP. This is longest increasing subsequence, LIS. So how do we do this? So we want a tree map of integer to integer map, this new tree map. We're gonna get roasted for this log factor. That's gonna be brutal. I'm not excited about that. Yeah, how do you do? You can do it with just a tree map. So for int I and A. Int build off equals map.get. Okay, so map.lower entry at I. So if from val okay, so if this is, what are we doing here? If this is we're gonna have problems. This is definitely gonna TLE here. This is not gonna be okay. Okay. Longest increasing subsequence, Java. Is this n squared? Is this really n squared? Are they serious? Wait, this looks linear. Do they call? They do. It's n squared. Worthless. That's exponential. Okay, this is going to be n squared. Will you tell me the runtime? Okay, worthless. Wikipedia. So n log n, so that's a problem. Okay. Yeah, so I think this is just, we need to abuse the fact this is not an arbitrary array. Okay. Yeah, so I think this is gonna TLE. We should just finish this and then submit, I think. How many people are submitting? A bunch, so it's gonna TLE. But we might as well give it a shot and then we can think about it soon. Yeah, so this will TLE, but what are we doing here? So well map dot floor so we have this bigger element. If bigger dot get value is less than or equal to my val, then map dot remove bigger. Dot get key. Else break. Okay, so we should be fine there. Yeah, and then ans equals math.ans of ans in my val. What? Math.max of ans in my val. Yeah. No. All right. Oh, we never put it. So we knew build off dot put or map dot put I my val. 9, 17, 12, 29, 14, 39. Okay. How many test cases do we have? And the third. Let's try submitting. It'll fail, but we'll give it a shot. So now we need, oh, sorry about the noise. I'm making ice cubes, I guess. So this is gonna fail. This is gonna TLE. Or it might be a happy birthday present that we get it, but I'm fully expecting a TLE here. Because this is bad. Yeah. So we can do better by using the fact that there's like not many things we can build off of. Yeah, so we can do this in 20 minutes. So we can say like the answer is going to be just like some start indices. So we have like order n. Yeah, we have like we can do an n squared dp here. So we have order n important start indices. And then we're gonna pick like this start index, and etc. So we need like an n squared LCP. We could also do this with an RMQ if we needed to, but this is just easier to just do it like this. So we'll have for all pairs, what's the LCP between these whole pairs? And then we'll say if you pick this and come from this, you get all of these strings like from the previous one. So then you start getting these ones here. So we do the n squared LCP, and then we do a DP at which position you're at. And then this has a linear transition. Yeah, so we're fine there. Okay, so then we shouldn't need this anymore. I guess let's make an E2 because we know E is right. So we'll get rid of this. We need some more, a little bit lame. Oh, so this is actually just way easier than what I was trying to code up. Yeah, I think. Okay, so we want let's just get rid of this. We don't need the stack. We don't need A. We don't need this. Okay. So int array LCP2 gives me int array n by n. For int I equals 0 less than n I plus plus. Int j equals I plus 1. J is less than, oh my goodness, j is less than n, j plus plus. Else, or int ans equals integer dot max value, and then ans equals math dot min of ans and LCP at j minus 1. Okay, and then LCP2 at ij equals ans. LCP2 at I to I equals n minus this. Is this true? So we are ourself. N is length of the string, suffix array at I is the start index. Yeah, I think that's fine. Okay, so now we have all of our LCPs. So now we need int array dp, this new int array, this is just linear, int array n. Yeah. We want which starting position we're at. Yeah. So okay, so for this DP, we need to say for int start, or I guess, yeah, int start equals n minus 1. Start is less or greater than or equal to 0, start minus minus. So this is where we're at, and then dp start equals something. The final thing will be So this is if we build off of the prefix starting here. So we want to build off any later prefix, but we can only do it if it's after us in the suffix array. Yeah. So we want int max next equals 0, max next plus, I guess max transition, I guess. So max transition would be just our length, right? So this is just n minus start. Yeah, okay. So for int 2 equals start plus 1, 2 is less than n, 2 plus plus. So int LCP to lose will be LCP2 from start 2. And then int get from me will be max transition. No, will be n minus start. And then int get from him will be dp. Oh, so we only want to do this. So if index of at 2 is greater than index of at start, then we can do this. So he has to be after me in the LCP array, or in the suffix array. So then we look at, this is how much we lose because we share it. This is how much he gets from me. Yeah. And int get from him will be just dp at 2. Nine, 17, 12, 29. Oh, did I get it wrong? 29, 14. Oh, no, 9, 17, 12. Okay, I say 25. Yeah, this is 29. Do I get the last two right at least? Okay, so I get this one wrong. So this one is it's 25, but what do I say? Or it's 29, but I say 25. You can beat me. Really? That's so long. Oh man, that's so long. Is it not necessarily true that these are continuous starts? Like, why wouldn't it be, though? The closest thing to you is just a prefix of you with one fewer letter. Right? You might as well make that as close to you as possible. Right? I think so. Like, okay, so the only messy part with this is this stack. Like when I'm doing the stack thing, some shenanigans can happen there. I'm getting an answer that's too small. Yeah, so it's just, you just need the first index to be sorted. Why would this be wrong? I have a break case too, even. Maybe we can get a smaller one. So what if we have like, okay, good. There you go. Okay, 1 for ABAB. Good, okay. What about 1, 3, ABA? Oh my goodness, okay, so easy. So, well, let's look at this, this is easy. ABA. ABA, so we have A, AB, ABA, BA, or B, BA, and then A. So we can pick these 5, right? And then, what am I getting? I'm getting 4. Why am I getting 4? Why am I getting 4? DP at 2 to 1, okay, that's right, to 2. Okay, so this is considering from to 2, this is start with plus LCP to lose plus get from me plus get from him. So considering 0 to 1, so I lose, why do I lose 1? You should not lose 1. Oh, this should be, yeah. This should be index of. Good. Okay, so this will be fine, I think. $28.14. Oh no, bro. Okay, we got the second case wrong here. Really? Okay. So, do we pass this now? 9, 9. Abacaba? What about Abacaba? That's 7. 17. 17, okay. $16, 17. All right, so yeah, I guess what is it here? This is so long. How much time do we have? 3 minutes. It's obnoxious. Okay. So why is this the case? And this is like 2 contests in a row. I'm in the exact same position. Oh, should this be SA? Yeah. I think I'm going backwards here. Do I pass? Okay. Yeah, that seems fine. So, how many test cases? Not many, so we should be good here actually. Should be fine. Ooh. A little close for comfort. What do you think? I think I'm gonna TLE. It's gonna be dumb. What can we speed up? This here? This LCP thing, so max and min. This should be fast though. This should be very quick, yeah. All right. All right. Yeah, that's our contest. That's it. Not bad, 61st place? Not bad, not bad. All right, yeah, we don't have time to get F, so I think that's not terrible. Pretty good, I think. BK, son. And game. Let's go. Are these TLEs? Yeah. They're doing it naively. The naive doesn't work, guys. Runtime of 10 to the 9. You gotta speed it up a bit, you know what I mean? Okay, so let's do solutions. Talk about solutions. Sounds good. Awesome. Okay, we need that. Okay, yeah. So solution time. We'll start with problem A. Close all these tabs. Man, that's really satisfying to do, isn't it? Ooh. Okay, start with problem A. The miracle and sleeper. So we have two integers, L and R, and we want to find the largest possible value of A mod B over all pairs A of B of integers. So, yeah, I don't really have a proof for this, but like, we have B, right? We want to get the answer as close to B minus 1 as possible. The answer, so okay, so you've got some, let's do an example here. Maybe you choose the integers like 3 and 13. So if you choose these integers, then your answer is going to be this bigger one mod the smaller one, which is equal to 1. So 13 modulo 3 is equal to 1, because 13 divided by 3 is 4, remainder 1. So you want the remainder to be as big as possible. So the answer is always going to be smaller than this. In fact, it's always going to be, the biggest it can be is like, this is going to get, we're subtracting out some number from it. So the biggest this can be is like n over 2 minus 1, right? It can't be n over 2. I guess it can be floor of n over 2. This is like the biggest it could possibly be. So we want where n is the second number. So we want the second number to be as big as possible, because then our answer will be like, it could be bigger. And then we want this to be some number that makes our answer as close to possible as this. So if this is really close to this, we want it to be smaller. But once it hits a certain point, we'll hit the best answer we can get, and then making it smaller will only make our answer worse. So yeah, in this case, if n is 13, we can consider what values of A could we pick. So we could pick like 12, 11, 10, 9, 8, 7, 6, 5, and so on. If we pick 12, we'll get a remainder of 1. If we pick 11, we'll get a remainder of 2, 9 a remainder of 3, 8 a remainder of 4. If we pick 7, nope, JK, yeah, 7 will get a remainder of 5, because 13 divided by 7 is 1 remainder 5. But if we pick 6, then we'll get a remainder of 1, because this is equal to 13 divided by 6 is 2 remainder 1. So we want this, which is as big as it'll get, ever. And this is always equal to 13 over 2 floored plus 1. That's this A that we want to pick. So we'll leave B the same, and then we'll make A as close to possible as close as possible to this, and that'll be your answer. So here's what that looks like in code. Yeah, pretty simple. And that's the solution. That's problem A. That easy, guys. That easy. Bro, what happened to my screen? This is obnoxious. This is obnoxious. I look really dumb in this picture too, don't I? That's kind of funny. Hi. Hi. Awesome. I wonder how long it was like that. You know what I should do? I should get a second monitor so that kind of thing doesn't happen. That's what I should do. Or at least when that kind of thing happens, I notice. I should really get a better card so that I can use this camera without it bugging out on me. Okay. Anyway, that was a good contest though, so I think I'll still have to upload the video. Okay. Well, there you go. There you go. You win some, you lose some. Problem B. Sorry about that, guys. I worked so hard to make the video quality better today. Oh, I'm sorry. I'm sorry. Well, we'll move on to problem B here. Nothing I can do now. I mean, I could re-record it, but that's a lot of work. Okay, during a hypnosis session, Yeah, so we have some integer n, and we want to know if we remove some digits, what's the maximum number of digits that we can remove, so that we, at the end, have some number that isn't prime. So I guess one observation is that it is possible to go from a number that's prime to a number that isn't. If you consider some number like, I don't know, 27. 27 is prime. 23. Look at that. I'm turning 23 today. Perfect. 23 is prime. So I'm back in my prime. Awesome. Gotta love it. 23 is prime. You can turn it into 2, so you can make a prime number not prime, is the important observation here. Yeah. Cool. So, awesome. So yeah, so that's the idea. So the important observation here is if your number contains any of these digits, if it contains a 1, a 2, a 4, a 6, an 8, or a 9, then the answer will be 1. You can just keep that one digit and it won't be prime. So the only digits that aren't on this list are 3, 5, 7, and 9. So you have these 4 numbers that aren't on the list. And if you look at the numbers 33, 55, 77, or 99, each of these numbers are all composite. So you can't use any pair, like you can only use each number in this list once. If you use any number twice, then you'll be able to reach one of these. So the only possible choices that you have are you can use each one of these once at most, which means if you ever have 5 digits, if you have greater than or equal to 5 digits, there is some number you can reach that has 4 or less digits, 4 or fewer, and you can find that, right? There will be a composite number you can reach with 4 digits or fewer. Or it's possible you can't reach anything, but they guarantee that won't be the case. So you only have to check numbers up to 100,000, right? You just check every number up to 9999. No, you can't even have 9. Because 9 is 3 times 3. So the only numbers you can have are 3, 5, and 7. So this only needs to be 4 digits. Yeah, so you can, so you only need to check, there are only 3 digits here. Yeah, 3, 5, 7, yeah. So each of these numbers are multiples of 11, which means you only need to check, all numbers up to 999, right? And you just need to check, okay, there will be some number between 1 and 1,000, or between 1 and 10,000. There will be some number between 1 and 10,000 that will divide this number. That's always the case. So you can just check all of them. There aren't that many test cases. You check all of them. And then your runtime is like 10 to the 7 times the way to check if it's an LCP. So you can do it faster, but I just did 10 to the 7 times 50, I think. Is that too big? No, the sum of k is 10 to the 4, so it's just 10 to the 4 times 50. So very easy. Yeah, 10 to the 4 times 50. Or 10 to the 4 times, well, this is 10 to the 4, isn't it? Yeah, for each of these, we find one of these. So it might be a little bit slower. It might be possible to hack my solution for this, but it's like, it's pretty easy. Like, you can just, there are very few combinations that you won't find it very quickly, so you can just like pre-comp those. And yeah, the idea is just, the important idea here is that there's always a small answer, right? The answer will always exist. You'll always find an answer with 4 digits or fewer. And you'll find it pretty quick. So you can just check things naively, and then you're looking for some non-prime number that's a factor, right? And you just check in increasing order. The first one you find will be the solution. So yeah, that's the idea. Okay. Here's what the code for that looks like. So first I pre-compute all prime numbers. I just do this naively. You could use a prime sieve, but I just do a prime check for each number because you don't really need to be fast. And then I get the number that we're looking at here. and I just check small numbers until I find one that works. And they guarantee that you'll find one in the problem, and then I print it at the end. So it should be pretty fast, I think. But I guess we'll see if I fail system tests. Looks like I didn't, so we're good. All right, problem C, rings. Yeah, so this is a really cool problem. I actually really like this. So what you're given is some binary string. It was a bit difficult to read, to be fair. This could have been explained better, I think. But here's the problem. So you're given some binary ones and zeros, like this maybe. And what you want to do is, so in this case, the length is 8. There are 8 numbers here. So you want to find 2 substrings that are each greater than or equal to 4 in length. So maybe you pick this substring here, and then you pick this substring here. Maybe this one here. So you have one of length 4, one of length 5. In this case, if you read these as decimal numbers, this number here will be 1 plus 2 plus 8, which is equal to 11. And this number will be 1 plus 2 plus 4 plus 16, which is 23. So in this case, it isn't true, but what you would want is 11 to be a factor of 23. And you want to see how is it possible to do that? How do you get 11 to be a factor of 23? So you want to pick any 2 strings where both strings are at least half the length of the string minus 1, or like half the length floored. And then you want one in decimal to be a multiple of the other in decimal. If you were to like read it as a binary number. Okay, so there you go. Now here is some quick observation here that we can use. We only care about like a pretty small subset of things. So what we're interested in here is if, like, here's some observations. So if you've got some binary number, right, like this maybe, if we add a 1 to the end, that's the same as multiplying it by 2. In decimal, in base 10, adding a 0 here, sorry, adding a 0 is the same as multiplying it by 10, but in binary, it's the same as multiplying it by 2, which should be pretty straightforward. Also, the other obvious thing is if you add a 0 to the front, it doesn't change the value of a number. So what we'll look for is, let's look for strings where we can have some string, doesn't really matter what it is, just needs to be long enough. And then we'll have this as the first string, and the second string will just have something at the end. And that'll be, obviously, the first one will be a factor of the other. Or we can have 0 in the beginning, and then the 2 values are equal. So that works. So the question is, when can we find strings that are long enough that have this property? And we'll almost always find something like this. In fact, if you have any 0 in the entire array, if the 0 is in the first half of the array, you can choose these 2. And if the 0 is in the second half of the array, like this, you can choose this string and this string. And the shorter of them will always be n over 2 floored, at least. So we can solve this problem for any array that has at least 1 0 in it. And that makes the rest of the problem really easy. So now we know the array is all 1s. And it might be, okay, well, this sounds difficult, right? Each of these are like a power of 2 minus 1, right? So this is like 8 plus 4 plus 2 plus 1 would be 15, right? And 15 is like a weird number. It probably doesn't have that many factors that are of the similar form. So what you can do is just say, well, instead of trying to pick 2 different numbers, we'll just pick the same number, right? So you pick a 4 and then a 4, a 4 and a 4 like this, for instance. Or you can just pick, these 2 strings, is what I did. Because you know the array is all 1s, so just pick 2 substrings that are all 1s, and that works. So those are the 2 cases. Awesome, hopefully that made sense. Yeah, it's really easy. I just have this print method, and then if there is a 0 in the array, then, or if there is no 0, then I print the first n minus 1 things and the last n minus 1 things. Otherwise, I print, if the 0 is in the first half, I print the 0 to the end and then 1 after the 0 to the end. Otherwise, I print the beginning to the 0 and then the beginning to 1 before the 0. And you have to, I don't know if I mentioned this in my explanation, but you have to print it so that the bigger of the 2 numbers, the one that is a multiple of the other, comes first. It doesn't matter if they're equal, obviously, but if they're not, and I guess it doesn't matter for this case either because they're equal again, but in this case you have to get the order right. So you have to just be careful there because it'll be like times 2, right? So one is actually bigger than the other potentially, assuming it's not all zeros. So yeah, be careful there. Okay, that's problem C. Moving on, let's do problem D real quick. So yeah, I'm just gonna talk about the solution to D2 to save some time here because I don't think it was that much more difficult. But one thing you can notice is like, yeah, let's talk about the problem here. So you've got some pluses and minuses. Basically they're plus 1s and minus 1s, like this. And what you're gonna do is you're going to imagine you have some of these. You're going to, once you have this, you're gonna like flip every other. So after, okay, these were all minuses. Let's make it a bit more interesting. Let's make this one a plus. So you're gonna flip every other, and then after that you'll have plus, 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 minus, minus, plus, plus, minus. Did I get that right? I think so. Yeah, so you flip every other one, and now you wanna see, okay, you want the sum of these numbers to be 0. Where a plus means plus 1 and a minus means minus 1. In this case, the sum is not 0. The sum is 6 minus 3, which is equal to 3. So that means this initial group didn't work. So we would have to remove some elements from this initial group so that after we flipped every other, the sum would be 0. An important thing here is if you were to remove something, like let's say you remove this, this changes which ones you flip. So yeah, it would go from being that to being this here. These would be the ones we flip. And that would change stuff in some way. I think, no, this wouldn't work. Okay. So a couple observations here. The first is at the end, if you want the sum to be 0 and you're adding a bunch of 1s, plus 1s and minus 1s, obviously you want an even number of things, because whether your sum is even or odd will change at every step. So you need to have an even number of things left over, which means initially, if it's even and doesn't work, you have to remove at least 2 things, because you have to change it, and you need to have an even number of things at the end. If it's odd and it doesn't work, you have to remove at least 1 thing because you have to change it. So that's a lower bound. We can easily say we need to remove those many things. And it turns out, with just that observation, we can solve problem D1, because it's always possible by doing that. And you can, samples are so good, in fact. They're so generous, which is very nice of them. I really appreciate that. Oops, let's look at D1. Samples are so nice. We got so many of them, so many queries, that we should be able to see this from samples, right? Just like notice the pattern here. These are all 1s, 0s, and 2s. So just like notice that and then be like, oh, well, it's pretty easy to tell whether it's a 0, and it's pretty easy to tell whether it's a 1 or a 2. So that's the first observation, which we'll prove in a moment when we actually solve it. So how do you check if the answer is 0? Well, we can just say, in this initial array, rather than just storing the array, we'll store the flipped versions of each of these. And now we can say, okay, if they give us some range to query, let's say they're interested in these perhaps. Well, okay, that's 5 long, so let's say they're interested in these 4. Now, we want to check if this range sum is equal to 0. So what I'm doing here is I would check if the range sum is equal to 0, but really, like, if we were to actually look at these things, the ones that would be flipped would be the other ones, right? We wouldn't flip the second and fourth, we'd flip the, or I guess we would flip the second and fourth. But you can imagine for this query here, we wouldn't actually flip the first and third, we would flip these 2. But it doesn't matter, because if the sum is 0, if we flipped the ones we didn't flip, it would just, the sum would be the negative version of the sum, and negative 0 is the same as 0. So this works fine. So for D1, the solution is super clean. We just say, we build a cumulative sum array of all of the numbers here, and then we say, find the cumulative sum. If the answer is 0, print 0. Otherwise, if the answer is even, print 2, or if the answer is odd, print 1. Okay, so that's the solution to D1. You can kind of see that even without knowing much about the problem, which I think was maybe cool, maybe it's interesting. But definitely you need a problem D2 in the set, otherwise the geniusness of this problem just gets lost. So I think this is a very useful case of having two versions of the same problem in the set. Okay, so cool. We've got D2. What do we do to actually solve this? So now the question is, how do we find this answer? And here's the observation. When you have some number, right? When you have some number you're going to flip. Let's say we're going to flip this number here. What's going to happen is you have these numbers will have some prefix sum, right? In this case, these numbers add up to 3. We want these numbers after us. After we remove ourselves, we want these to add up to -3. But we're going to delete this, which means we're going to change the offset of which numbers get flipped. So initially, we want the sum to add up to 3. Because then when we remove ourselves, the sum here will get inverted. Everything that's a plus will change to a minus and vice versa. So it'll flip like this. So then once the sum is then -3, -3 plus 3 will be 0. So in total, we'll have a sum of 0. That's what we're going for. So we want to pick some number. If initially the sum is 7, we want to pick some number where the sum is 3. Or sorry, where the sum is 4. Because then we'll have 3 before us, we'll have a sum of 3 after us, and then we'll remove ourselves. So this will change to -3, and that'll be exactly the answer we're looking for. Implementing this is actually quite easy. All we need to do is go from the right and say, when is the last time the prefix sum was this value? Right, so we just want to say, okay, if we imagine we're at this position, we want to say when's the next time the prefix sum is whatever. We can just process all of our queries offline and answer them by left endpoint from right to left. And then we'll keep track of, we'll have some array where we keep track of what was the value, what was the last index that the prefix sum was this value. And then as we move left, we can maintain that array. So yeah, that's the idea. The code looks kind of like this. So we have a bunch of stuff going on here, but we read in the array, we build our cumulative sum array, and then we make all of our queries. And then we're going to process our query by their left endpoint. So we have a list of all queries that end at a certain left endpoint. And then we're going to go from left to right, or from right to left, and look at the left endpoint. And then we mark when the next time the prefix sum is this value. Now I'm using this offset, so all the indices are positive, but you could probably get away with just using a hash map, and that would be fine too. So you don't need this offset if that looks kind of messy to you. And then we have this query, and we see if the query already works, the answer is 0. Otherwise, if it's too long, so if you're, I guess this is the case I didn't really cover, if you have to remove 2 things, like that would be kind of annoying. So here I'm assuming the sum is going to be odd. But if we know we're going to have to remove 2 things, we might as well just remove the last one and then say, okay, well, we removed the last one, now we can do it in 1 here, right? And that doesn't, like, it's a perfectly good answer. It's a perfectly good way of doing it. But you could also like remove the first thing always and then something here, but then it kind of flips things, so it's a little more difficult to think about maybe. So I thought it was easiest just to remove the last one. I think it's probably also true you can always remove 2 consecutive elements. I think that's true. I have not fact-checked myself on it, but yeah, that might be another easy way of doing it, but this requires almost no special casing, right? Because if you just remove the rightmost endpoint, then it's always going to be odd in length. Okay, so now we get the final sum of the array. In the example I was giving earlier, it was 7. And then we want to find when it's the target sum. So this might be 7, it might also be -7. So the target sum is going to be either 4 or -4. And then we want to find when's the next time it's that, but it's a cumulative sum index, so I need to subtract 1 here. And that is the first number that I remove. The second number might be the last element in the range. And finally, I print the answer at the end. Awesome. Yeah, so that is problem D. Cool. Finally, problem E. Let's do this. So problem E, rescue Nguyen. Yeah, this problem. Okay, so this is a little bit more difficult to explain, but it's not hard to code at all. So for this problem, you have, the statement actually does a pretty good job of explaining it, I think. It's a kind of complicated operation, but you're looking at all substrings of some given string, and they're given in like an order that an n-squared for loop would work in. So you have like you kind of like start with the prefix. You look at all the prefixes of the substring starting at index 1, then all the prefixes of the substring starting at index 2, and then index 3, and index 4, and index 5. So you have like a list called like an expansion of some string. You have a list of all of these. And now you want to find the longest increasing subsequence of this list. Yeah, that's the idea. You just want the size of it. You don't need to actually print the list because that would be pretty big, right? The list could have theoretically like n squared things in it, I think. So each one of those could be length n, so there could be n cubed total length if you wanted to print all of them, which would be pretty tough. So you can't do that, so you just want to print the length. So here's the idea. What you could actually do if you wanted is just generate the array by giving each of these strings some value. And you can do that with suffix arrays. And we're still going to use suffix arrays here, but we're going to be a little bit smarter about it. So here's the observation. Let's say we're going to use some string here. Maybe your string is like A, B, A, C, A, B. Abacab. If we want to find the first string smaller than this lexigraphically, that's going to be equal to A, B, A, C, A. We might as well use this string before us. Is that true? That's not true. We might have A, B, we might have this. Yeah, okay, so it's not true. So let me say this in a way that is true. Okay, so let's only look at like the maximal length strings that we pick. So we're gonna pick strings that might be like, maybe we pick this string here, and then maybe we pick this string here, and then maybe we pick some set of substrings of these maximal strings. But let's only worry about the maximal strings we pick. So like we pick this one and we pick this one, for instance. And interestingly, all of the maximal strings we pick are their right endpoint is gonna be the right end of the array, right? There's no reason to pick like, if we pick A, B, A, and then afterwards there's a C in the array, there's no reason for us to use the string A, B, A, but not use A, B, A, C. So we're gonna pick like a bunch of suffixes of the root string. I guess we'll use an example here. So let's say AC, AC, B, AC. So yeah, so let's say the maximal strings we're gonna use are gonna be this one, AC, B, AC, and then we'll use C, B, AC. Say these are the two maximal strings we're gonna use. So these are like, they both are suffixes of the initial string. And then the strings that we can pick from this are A, AC, or AAC, ACB, ACBA, ACBAC, and then C, CB. We'll just finish this for completeness. CBA and CBAC. These are the 9 different ones we can pick. This is the same as the sample. So yeah, like it should be pretty clear that we always want to pick suffixes of the initial string as our maximum string. And then it should also be clear, I think, that anytime we want to pick a suffix of the maximum string, we want to pick every prefix of that suffix. So our answer is always going to look something like this. Now, there's a little bit of a caveat here. We might have something like this. We might have A, B. This is a good example. So if we have AAB, really we want to pick all suffixes, right? We want to pick this here, we want to pick this here, and then we want to pick this. The problem is, if we did this naively, we would pick A, B, then we'd pick these ones. So we'd pick A, B. I think you see the problem here, and then we pick B at the end. The issue is we've picked this twice, and this string here it belongs earlier. So we have to skip this. We don't want to pick this. And we can do this by storing the longest common prefix of 2 strings in a suffix array. So if you imagine we have each of these suffixes sorted, we can do this in n log n time using suffix arrays. This is a well-known technique. And then with our suffix arrays, we can get the longest common prefix between any two adjacent suffixes in this sorted list. So once we have that, we can use this like longest common prefix array and do some stuff with it. And that will give us the strings we should skip. So the longest common prefix between two adjacent so like the LCP for this array would look, or the suffix array for this array would look like this. So we would have AB, then AB, and then B, which is initially because it's initially sorted, so it's pretty simple in this case. But the longest common prefix between these two is 1 because this A is shared. The longest common prefix between these two is 0 because they don't share any characters in a prefix. So what this indicates to us is that if we're going to end up doing a DP, but if we do a DP for this possible answer, we want to say, okay, we can build off anything we want to in the future. Let's build off of this AB here. So we can use this future answer here, and because this is both later than us and after us in the suffix array. And then we say, we can use this entire answer except stuff that is also a prefix of us. So in this case, this A would also be a prefix. So we need to say like dp of us equals dp of us, or like this is like the length of us, plus the dp of whatever we're going to, minus the longest common prefix. Yeah, so this is like one possible transition, and we'll try going to all future possible suffixes. Hopefully that made sense. The code for it I'll show right here. So this is like the naive brute forcer, I guess, which has an extra log factor, so it's too slow. But this is what that looks like. So I calculate the longest common. This is just built-in HECPACK code. It'll get the suffix arrays. Sorry, this is get the suffix arrays, and I don't need the stack. This will get the suffix array. I don't need that either. Interesting. Okay. This will get the suffix arrays and the longest common prefix, and it does both of these in n log n. And then after that, I get the longest common prefix between any two substrings in the array. And then I just do the DP. So the DP brute force is what I'm at. It goes in the order of the suffixes from right to left in the initial array. And then I look at every other possible suffix that's after me. I might build off any of those. And I can if it is lexicographically bigger than me. So I can check that here real quick. You could also probably just do this. No, you have to do this in order 1. So yeah, this is the best I know how to do it. And there you go. Just take the best answer and put it at the end. Okay, hopefully that made sense. That's all from me for this contest. And yeah, hopefully, I don't know, I'm sorry about the webcam issue. I don't know, I have to figure that out. That'll be some work. But yeah, anyway, I enjoyed the contest. Hopefully you did too. And if it was rated for you, hopefully you got a good rating boost. Anyway, have a great day. See you in the next contest.